We are continuing with our hypothesis testing, and we are now proceeding to the practical part where we are going to do testing for means. You may recall that when we are testing differences in means between the two categorical variables, we can use a t-test for two groups, or we can use ANOVA if the groups are more than two. In both cases, there are some assumptions that, first of all, the populations in the groups that are being tested are normally distributed, and that the variable that is being tested across the two groups has equal variances. And I need to emphasize something here. Equality of variances does not mean point equality, that the variance in one group is exactly equal under point estimation to the variance in another group. What it means that the variances are not statistically significantly different. And in every hypothesis testing for differences in means between the two categorical variables, one of the things we have to do is to test for equality of variances. This assumption is quite important because if the variances are found to be equal, in other words, not statistically different, then we use the pooled variance. Then we pull the variance from one group and the variance in another group and come up with a common variance that we use for hypothesis testing. However, if the variances are different, statistically different, then we use individual variance. Each group uses its own variance. And the way we compare, or the way we assess equality of variances, we conduct a test known as a variance ratio test. Variance in group 1 divided by variance in group 2. If the variances are equal, that ratio is going to be equal to 1. If the variances are not equal, that ratio will be different from 1, and the statistical test will indicate that it's statistically significantly different from 1. And we shall see that as we go along. Now I want to turn your attention to the slide. And as you can see, first we assume that the populations are normal, and if you have to test normality, if you can test it, please, it is always good to go ahead and test for the normality of the normal distribution and see whether the variables you are going to test in those populations are normally distributed. Then the second assumption we talked about is equal variance. Sigma squared 1 variance in group 1, we assume is equal to variance in group 2, and therefore these can be pulled into one variance. So the question usually is whether two categorical groups differ by a continuous variable. And take the example, this question, is there a difference in the mean anxiety score between the two groups? So the mean anxiety, this is mu1 mean anxiety score for group 1, mu2 mean anxiety score for group 2. Recall that in the previous session, we indicated that once we set the null hypothesis, that one statistic is equal to another, and the alternative that they are not equal, this automatically indicates that this is a two-sided test. And here we are using the t rather than the z because we don't know the population variance, and we may not be sure about the size of the groups. Remember that once we know the population variance, then we can actually, the parameter, not the statistic, the parameter population variance, then we can use a z statistic. But also if the sample size is big, 500 and above, some textbooks say 200. In my experience, I find 500 better. Then even if we don't know the population variance, but the sample size, combined sample size, is equal to or greater than 500, then we can still use a z. If those two conditions are not satisfied, then we use a t statistic. So how do we pull the variance? Now, I did say earlier on that we conduct a variance ratio test. And the variance ratio test is to compare variance in one group divided by variance in another group to test the assumption of equality of variances. Now, if the variances are not statistically significantly different, then we use the pooled variance. And you can do the pool, you can actually pool the variance yourself manually using this formula. Sample size for group 1 minus 1 times the variance of group 1 plus sample size for group 2 minus 1 times the variance of group 2 divided by the degrees of freedom, which is sample size for group 1 plus sample size for group 2 minus 2. However, if you are using a software program like a SAS or Stata, it will actually assess it, compute it, and see whether the variances are different or not. And so this is very important. So the decision, as I mentioned, the decision on whether to use a pooled variance or not depends on whether the variance ratio test shows us whether the variances are statistically equal or statistically unequal. And so there are different formulas you can see in your slides that we use for the Z statistic and for the T statistic. And we calculate the observed Z or the observed T and compare it with the Z in the tables or the T in the tables. And we are going to now look at these two examples. And I want to turn you back to the slides again. So usually, questions come in this kind of format. In an assessment of UPE and private upcountry schools in Uganda, the mean aggregate score at PLE was 8.6 with a standard deviation of 2.4 among 230 UPE pupils, 7.1 with standard deviation of 2.1 among 180 pupils in private schools. Can we conclude from this data that the mean aggregate score differs by type of school? So the question on hypothesis testing will not come by saying, here is the N1, variance 1 SD1, N2, variance 2 SD2. Can you please test the hypothesis to see if these two means or proportions are equal? No, they won't come in that format. They usually come in the format that we have on the slide. And we have many other examples. We actually have 4 examples on the slide. Now, if we go back to the slide, we now, because we have 2 groups, we use a t-test because we are testing whether in a continuous variable, in which case scores at PLE differs by categories of school, whether it is private or UPE. So in Stata, we use the following commands. And these are immediate commands. When you don't have the data in the memory, that's when we use the immediate commands. But if the data are in the memory, we don't use the immediate commands. In other words, we do SD test I. This is immediate. That means that you have not opened your file in Stata, but you are now using Stata as a calculator. That's why you put the I to indicate immediate. So once we use the immediate command, then we give the number of observations, then we give the mean number of observations for group 1, mean for group 1, and then we give the standard deviation, and then we do the same thing for group, we do that of group 1 and group 2. Then this SD test I is the one that is testing the standard deviation. This is the command for the variance ratio test. Then after that, we now go to the command for the t-test, which is t-test I. And again, this is one group, and this is for 2 groups. Please note that when we do t-test I, or t-test if the data are opened in Stata and in memory, then the default for Stata is equivariances. So if you've done an SD test and it shows that the variances are equal, then you just do t-test and you don't add anything at the end because the default for the computer is equivariances. But if you've done an SD test and the variances are unequal, then you have to change from the default by putting a comma and telling stator unequal, so that now it knows that it's going to do the calculations or the computations based on unequal variances. Okay, so these are the commands when the data are in memory. We are now no longer using the immediate commands. You notice that the i's have gone. Here is when we have a data set already in memory and we open it in stator. The only difference between this one and the previous is that we don't have the i's. And the second difference is that instead of now stating the number of observations, the variance and what, here we just state the variable. This is the variable name that we want to test. And while we are still on the slides, let us go back to our first example of UPE performance at PLE. Now, using the SD test I, where this data set is not in memory, so we do SD test I, we give N1, which is 230, variance, the mean x bar is 8.6, its variance is 2.4. Afterwards, we put a space, then we put the N for the private schools or group 2, its mean and its variance, its standard deviation. Then Starter does the computations. Now, what we are interested in is this is the null hypothesis, that the ratio is equal to 1. But there are 3 alternative hypotheses. This in the middle is the alternative hypothesis that the ratio is not equal to 1. This exclamation mark means not equal in Starter. It is not. So if it comes before equal, it means not equal. The same thing can be done using the tilde sign, and tilde is what you normally call the approximation sign. So if you put the command in Starter and say tilde or exclamation mark, both these, each of these means not equal. Even this one means not equal. So in Starter, either you will use tilde or you will use the exclamation mark before the equal. The two mean not equal. So in this case, Starter is using the exclamation mark. And if we go back to the slide, you can now see that the null hypothesis is equal. The two-sided of not equal is this one. This is where we are going to interpret. And this 2 minus probability that f is greater than f, this is the p-value, but written in statistical terms. So the p-value is 0.2221. The alpha that we are using to test this hypothesis is 0.05. So our p-value is greater than alpha, and once the p-value is greater than alpha, then we fail to reject the null hypothesis. The null hypothesis which shows that the variances are equal. So the conclusion here is that we have no evidence that the variances are unequal. In other words, the data show, the variance ratio test shows that the variances are statistically equal. So now when we do a t-test, after doing a variance ratio test, we shall not need to put comma unequal. Why? Because we have evidence that the variances are statistically the same. So now if we move to the t-test, all we need to do is to change from here SD test, delete SD and put t, and then we now go to t-test I. Everything is the same. N1, x bar 1, SD1. N2, x bar 2, SD2. And now the null hypothesis is that the difference, and the difference is here, the mean of group 1x minus the mean of group 2 is equal to 0. Meaning that the mean in group 1 is equal to the mean in group 2. And again, the two-sided test here, or alternative for two-sided, is that the difference is not equal to 0, meaning the mean in group X is not equal to the mean in group Y. And look what we find. Our p-value is less than 0.05, the alpha, the default alpha, meaning that we reject the null hypothesis. Because if our p-value was greater than 0.05, then we would fail to reject. In fact, even if our p-value was exactly 0.05, we would still fail to reject. But if it is less than 0.05, which is our default in software, then we reject the null hypothesis of equal variances, and we conclude that, we reject the null hypothesis of equal means and conclude that the mean scores at PLE are not equal between these two groups. So we use the middle, which is two-sided. Because of the p-value that is less than 0.05, we reject the null hypothesis, and null hypothesis tests equal means, and we conclude that PLE scores are significantly different between UPE schools and the private schools. But which of the two groups has a higher mean? You see, the UPE this is data for UPE. So UPE schools have a higher score than private schools. So please note that in this case, the higher the score, the poorer the performance, because the best performance is aggregate 4. So anything that gets closer to 4 is better. So in this case, we have evidence to show that the private schools are performing statistically significantly better than UPE schools, because the means are different, and the mean for the private score is lower, is closer to 4 than the mean for the UPE schools. Okay, so we have other examples for other studies, like the one for the viral load test for a study that was done in Rakai, and that is also shown on your slides. Please follow the examples in the slide. You will be able to see the SD test for that viral load difference by HSV2 infection or non-HSV2 infection. And then you will see that when we do a T test using the immediate command, we also find that the p-value indicates that the two groups are statistically significantly different, and we now would ask you to make the conclusion for that one as part of your homework. Now, for the other example, example 3, the one which is by anxiety scores between boys and girls, you can also be able to do that. The commands are there for you, even the data is input already. The command is written for you. All you need to do is to open Stata and put in that information. First, you do an SD test I, which is a variance ratio test. Then, depending on how you interpret whether the variances are equal or unequal, then you do an SD test. Remember that for this example, you will have to decide whether you're going to add comma unequal or not. Or you're not going to add it based on the results of the variance ratio test. So please play around with this, practice it, and if you have any problems, go back to the worked examples. They are exactly in the same line. So this shows us the hypothesis testing for continuous variables of two groups. Recall from the beginning of this session that if the groups are more than 2, we cannot use a t-test. We have to use ANOVA. And from ANOVA, then you can move to linear regression as the case may be. So we now want to switch gears and move to hypothesis testing for proportions, because so far what we've covered has been for means. Please take time and do the third example before you proceed to the proportions part, because what you listen to you will recall about 15 to 20%. If you are very good at recalling, you recall about 30%. What you do, you will recall up to 90%. So please, if you have stata on your program, practice it using those commands. But even if you don't have stata, you have SPSS. There are still ways in which you can use SPSS and open SPSS and go to hypothesis testing. Then it will bring the dialog boxes and will ask you for sample size for group 1, you type it in. Ask you mean for group 1, you type it in. Ask you standard deviation for group 1, you type it in. Then it goes down and ask you the same information for group 2. Then you type it in. Then you click run, and then you will have the same information. In fact, all SPSS, now including stata, most programs are point click. You can just point and then you get the down arrow and then you choose. So SPSS, you go to hypothesis testing, then you go variance ratio test, put in that information, do the variance ratio test, interpret it, then proceed to do the t-test. And once you input the data, SPSS will ask you whether it is equal variance or unequal. SAS will not ask you for that. It will produce the two outputs. It will do the variance ratio test and produce the output with equal variance and the output with unequal variance. So it is up to you to decide. SAS will give you a buffet. It is up to you to decide what you are going to put on the plate and what you are going to interpret.